Rocio, even if talking about accurate and information, people have to hear them using Gaia DR3.
Okay. All right. Hi, everyone. Well, clearly I forgot which title I put for the talk, but I'm talking about the same thing. My name is Rocio Kiman. I'm a postdoc at Caltech, and I'm going to talk to you about the project that I've been working on that is, studying radius inflation on low mass stars using Gaia DR3. And in all of my amazing collaborators, Tim Brand, Jackie Faherty, and Mark Popenjak. So let's start by stating that ages of low mass stars, or M dwarfs, I might just use them interchangeably, is a current unresolved problem in astrophysics. So we have methods to measure ages of higher mass stars, which higher for me means higher than 0.6 solar masses. Those are methods like isochron fitting, astroseismology, gyrochronology, and empirical and statistical age relations. But when we go to the M dwarf, isochron fitting doesn't work. The luminosity and effective temperatures of M dwarfs change very little during its lifetime, so using that to estimate an age can be very imprecise. Astroseismology, there are no signs of pulsations on M dwarf yet, although theoretically they should pulsate, but in principle we haven't found them yet. Gyrochronology, we don't have a gyrochronology relation yet, but we do know that rotation is correlated with age. And then we are left with empirical and statistical age relations, which are key to understand the evolution of M dwarfs. And what do I mean by empirical and statistical age relations? I mean using different properties, and this is what I do in general, to estimate, using different properties that are correlated with age to estimate an age of an M dwarf. These properties can be such as color magnitude diagram position, kinematics, magnetic activity, and rotation periods, for example. But we know that all of these properties actually depend on fundamental properties of M dwarfs and other properties such as radius, mass, effective temperature, and metallicity. And when we start to understand and study all of these properties, we realize that, of course, those depend on age-dependent properties as well. So if we want to get a full idea of how the M dwarf evolved, we need to be able to estimate precise fundamental parameters. And today I'm going to talk to you about one in particular, that is the radius. So we know that there are problems with measurements of problems between measurements and models of radius and effective temperature. For that, I'm showing the work by Andrew Mann in 2015, where they are showing the difference in temperature between observation and model at the top, and the difference between model and observations in radius at the bottom. And we see that the data has lower values of temperatures, and the model predicts for the same mass, and the radius has larger values than what the model predicts, again, for the same mass. This problem is called radius inflation, and it says that the data is around 10% larger than what the models predict. So what we need is a way to estimate these parameters, the radius, mass, and temperature of M dwarfs, that are precise and model independent. And that's what we did. So we calibrated the surface brightness color relation using Gaia DR3 for masses for between 0.2 to 1.5 solar masses. So what we did was to grab a sample of stars with angular diameter measurements from Duver 2016 and cross-match that with Gaia DR3 to take advantage of this amazing catalog that is Gaia. So here I'm showing you in the y-axis the absolute magnitude in Kiman and the BP minus RP color in the x-axis. The sample of stars with angular diameter measurements is color-coded by metallicity, and is overplotted on top of the 100 parsec sample from Gaia. And in the small frame at the top is the distribution of metallicities of this sample. So taking advantage of Gaia, we made quality cuts to keep the best possible sample. And those quality cuts are the Rui number smaller than 1.4 to keep the most possible single stars and remove the possible binaries. Cuts on signal to noise ratio for photometry and parallax. We selected stars that were non-variable or classified as non-variable as single stars and to a distance less than 100 parsecs. That is to try not to care about extinction, so those stars will be less affected by extinction. So as probably everyone knows, binaries are extremely important when talking about studying the evolution of single stars. And in particular, my student Kent has been working on a definition of how to find binaries using parameters from Gaia DR3. And he's using this precise calibration to study the evolution of single stars of fast rotator in the field. So he has a poster Monday and Tuesday, so I'll encourage you to go and talk to him about it. And if you want to know more about rotation periods, stay tuned for the talk on Thursday by Seth Gossage, that is going to talk about our recalibration of the convective turnover times for M dwarfs, which should be very interesting. So go and look for that one. So going back to the surface brightness calibration, we started with the Stefan-Boltzmann law, and we included the angular diameter measurements, which is this theta parameter. We can approximate the volumetric flux as 10 to the minus 0.4, a magnitude times a polynomial of a color, and that polynomial is going to be the volumetric correction. Then we can approximate the temperature as another polynomial of the color, and the angular diameter is going to be approximated as 10 to the minus 0.4 magnitude, a polynomial of the color. And we can define this S magnitude to be able to calibrate the surface brightness color relation. So I know that I lose half of the audience every time that I put an equation on the slide, so I probably lost everyone. But the idea is there is a relation between angular diameter, magnitude, and color. If we can get that polynomial, we can find the correlation between all of the three. And that's the calibration that we did. So in the y-axis here, I have this S parameter that was calibrated in this case with the G magnitude, and in the x-axis is the VP minus RP color, and all of the sample with angular diameter measurements color-coded by metallicity are in the plot. And you can see our fit, which is a very tight relation all the way from F to M force, actually. So this is from 0.2 to 1.5 solar masses. We did the same calibration for all of the three Gaia magnitudes and all of the three Gaia colors. So we have 9 relations to be able to estimate angular diameters. So the idea is now, we have a color and a magnitude from Gaia. We can estimate an angular diameter, and combining that with a parallax, we can estimate a radius for anything that has color, magnitude, and parallax from Gaia. In particular, this relation was calibrated for the mass values that I just told you. So what we did was to use this radius to estimate the radius inflation problem on M dwarfs. And for that, we used the sample from Kiman et al. 2019. And what we did was to divide the sample in active and inactive. All of this sample has values of H alpha measurements. H alpha is a magnetic activity indicator for M dwarfs. And here in the plot, I'm showing you in the y-axis, the radius calculated by our method, and in the x-axis, the mass calculated by absolute K magnitude. In gray are all of the stars that are inactive, and in color-coded by H alpha are all of the stars that are active. So we can see right away that there is a clear difference on the average radius, where active stars have larger radius than inactive stars, which would indicate that magnetic activity is playing a big role in inflating all of the stars. So we see that at the higher mass end, the difference is around 7%, and this difference is getting smaller for lower masses, which was a known result also from before. So we are reproducing that result. So now we know there is an average difference. So can we calibrate how much this difference depends on the actual H alpha value? So for that, we calculated the difference between the active radius and the inactive radius divided by the inactive radius for different mass bands. So here I'm showing you the difference of radius in the y-axis, and in the x-axis, the H alpha values, the H alpha equivalent width. And I'm dividing it in several mass bands from 0.5 to 0.6, 0.4 to 0.5, 0.3 to 0.4, 0.2 to 0.3. So in principle, we found a clear correlation between this radius inflation and H alpha equivalent width for the higher mass band of H alpha, which would indicate that stars that are more active are more inflated than stars that are less active. And for the other mass bands, we see the inflation, so the star seems to be inflated, but we don't see a clear correlation with H alpha equivalent width. We cannot distinguish if this difference is due to that the relation is not there, but more likely is because the method that we designed, it has a 4% uncertainty to calculate the radius, which is getting closer to the actual value of inflation. So we probably cannot distinguish the actual trend because we just don't have enough precision. So talking about precision, I have 2 students that have been working with me and are going to continue working with me during the summer, Wally and Neha, that they are going to be working on actually finding pulsations on low mass stars. This is going to be extending to higher masses as well, and using those pulsations to calculate radius and effective temperatures. So Wally is working on a machine learning algorithm to do an unsupervised classification of light curves and seeing if we can use that to classify the test light curves as pulsators or not pulsators. And Neha is going to be studying a sample of a few hundred M dwarfs that we have with 20-second cadence data to see if we can actually find a signal of pulsations of M dwarf. We are pretty far from actually measuring parameters for M dwarfs, but in principle, looking for the pulsation itself. And this is work that we're doing with a lot of a great collaboration that is listed here. They have both together a poster on Wednesday, so I encourage you to all go and look for what they have been doing and what they are planning to do during the summer. So I'll leave my conclusions up, and I'm in the job market this year, so if you know of any opportunities, please let me know. Thank you very much.
Over here. Great talk. I love papers on fundamental properties. Your technique seems to rely on the Gaia color being a very good proxy for effective temperature. Have you considered what happens if it's the activity that means that the Gaia color is not a great proxy for effective temperature?
So yes, we are doing a lot of approximations of the temperature and, well, the volumetric correction on the color. And yes, the thing is that this work is based on a work that I did previously in Kiman in 2019 that actually showed that when looking at color, stars do actually look redder if they are more active, which I'm assuming is what you're referring to. And that is also correlated with the inflation. So I think that both of them, in that case at least, they are both saying the same thing. So when a star gets larger, the surface gets cooler and the color gets redder. The other thing that could be also, that could be more influencing the relation could be the variability, right? Magnetic activity generates a lot of variability. And for that, one test that I did was to show that Gaia is actually measuring a lot of photometry points. And to give you the last value is averaging over all of those photometry points. So that could take some of the dependence on the variability as well. This one or the other one?
And back then we had something like 3 or 5 in our system, maybe. And you asked a question. Yeah, so the idea was that maybe the inflation is caused by the different structure of the stars. So they are inflated because the magnetic dynamic is different in the larger stars than in the lower ones. So the change in the structure happens roughly at the 0.35 or so, and maybe that's the reason why they start being inflated.
Yeah, so the thing is that there's like a kind of a general continuous trend that goes from higher masses to lower masses, making the inflation smaller. In here, it looks like there's no inflation at the lower masses, but that's just an effect of the uncertainty that I mentioned, that this method has like a 4% uncertainty. Lower masses have been shown to have a larger inflation, like around the 4% inflation. And that is a continuous trend. Yeah.
Please make it quick.
Yeah.
Very short, but excellent talk. Thank you very much.
Thank you.
In relating this to HR activity, of course, the idea is that the underlying effect is because of conductivity. So, do you have any plans, or do you already have any information on what the magnetic field strength or the magnetic surface flux means? As the HR activity, it's a related question.
Well, these stars are quite faint. These are from the SDSS survey, so measuring the magnetic field flux might be a bit hard. And I don't know if there is a large enough sample to actually measure to do this type of Zeynam analysis. In here, as you can tell, I need a big number of stars to see the trend. I am thinking about correlating this with rotation period would actually help to extend it to higher masses. H alpha is not an activity indicator for higher mass stars, but a rotation period is, so that can help. And there has been a lot of very interesting work done by Guillermo Torres that they are actually measuring eclipsing binaries and with very precise measurements of the magnetic fields of those stars to see if they can correlate that. They have a very interesting paper in 2021 to correlate that to the inflation that they find in the stars. So that I think is probably the best way to go about it. I would just point out that this is for single stars, not eclipsing binary, which makes a big difference as well. Thank you.
Let's thank the speaker again.